Hello everyone and welcome. Today I am going to work through two fluid mechanics problems involving the momentum equation. So let's get started. So this is the first example. We have water flowing through a reducing elbow at 14 degrees per second. The elbow changes the flow direction by 30 degrees while reducing from 113 centimeter square at the inlet to 7 centimeter square at the outlet. We need to find the force required to hold this elbow in place. First, we find the water velocity at each location using the continuity equation. Mass flow rate equals density times area times velocity. At the inlet, the cross-sectional area is much larger, so the velocity is lower. With 14 kg per second flowing through 0.0113 meter square, we get V1 equals to 1.24 meter per second. At the outlet, the area is much smaller at 7 centimeter square. So water speeds up significantly to V2 equals to 20 meter per second. We use Bernoulli's equation to find the pressure difference. The pressure at the inlet plus the kinetic energy per volume equals the pressure at the outlet plus its kinetic energy adjusted for elevation. Working through the calculation with the velocity we found, the pressure difference from inlet to atmospheric outlet is 202.2 kilopascal. This is the gauge pressure pushing at the inlet. Now, we apply the momentum equation. The sum of forces equals the change in momentum flow rate. We have three forces acting. First, pressure force at the inlet pushing forward. Second, atmospheric pressure at the outlet, which cancels out in gauge pressure. Third, the anchoring force from the bolts holding the elbow. We break this into X and Z components since the flow turns 30 degrees. For the X direction, the anchoring force must balance the momentum change as water deflects. Plugging in our values, pressure force minus momentum change give us FRS equals to negative 2053 Newton. The negative sign tells us our assumed direction was wrong. The force actually pulls backward. For the Z direction, water deflects upward, creating an upward momentum change. This gives FRZ equals to 144 Newton upward. So the resultant anchoring force has two components, 2053 Newton in the negative X direction and 144 Newton in the positive Z direction. Next, we move to the example 6.4, water jet striking a moving cart. We have a water jet shooting at 35 meter per second that strikes the back of the cart moving at 10 meter per second in the same direction. The water flow rate is 30 kg per second. We need to find the braking force needed to keep the cart at constant speed, the power wasted by brakes, and what happens if the brakes fail. The water jet and cart are both moving in the same direction, so we need the relative velocity between them. The jet travels at 35 meter per second and the cart at 10 meter per second. So relative to the cart, the water approach at only 35 minus 10 equals to 25 meter per second. Think of it like sitting in the cart. The water seems slower because you're moving away from it. Even though 30 kg per second leaves the nozzle, not all of it hits the cart per second because the cart is moving away. We use the relative velocity to find the actual mass flow rate striking the cart. The formula gives us mass flow rate equals the nozzle rate times the relative velocity divided by the jet velocity. So 25 meter per second divided by 35 meter per second times 30 kg per second equals to 21.43 kg per second. Actually hits the cart. About 8.5 kg per second misses because the cart is moving away. Now we use the momentum equation. The sum of forces equals the change in momentum flow rate. The water arrives with velocity relative to the cart at 25 meter per second and leaves at essentially zero velocity. The forces acting are the braking force we're looking for and the force from the water jet pushing the cart forward. The brake force must balance the momentum change of the water. So the negative mass flow rate times the relative velocity gives us F brake equals to negative 536 Newton. The negative sign confirms the brake force opposes motion, acting backward while the water pushed forward with 536 Newton. Next, we calculate the power waste. Power equals force times velocity. The brakes apply 536 Newton while the cart moves at 10 meter per second. Power waste equals to 535.8 Newton times 10 meter per second equals to 5358 watt or 5.36 kilowatt. This energy is converted to heat in the brakes. It wastes because it could theoretically be used to generate electricity if we had a different setup, like a water turbine. The last one is, what if brakes fail? If the brakes fail, that 536 Newton force from the water jet will accelerate the cart forward instead of being balanced. Using Newton's second law, F equals to ma. So acceleration equals to force over mass. 535.8 Newton over 400 kilogram equals to 1.34 meter per second square. The cart will speed up. But here's the interesting part. As the cart accelerates and moves faster, the relative velocity between the jet and cart decreases, which means less water hits per second, reducing the force. Eventually, the cart could approach the jet speed, where almost no water hits it anymore. The acceleration is highest right at the moment the brakes fail. So that's all for today. Thank you for watching.